So, I remember what we left off on. I'm going to start with that this morning. So the last thing in your notes, I believe, is the 1 over r potential. Is that right? 1 over r, or 1 over x potential. And I related it, I wanted to relate that to gravity here in this room, okay? So that's what we're gonna start with. And then, yeah, we'll see where we go with that. So, recall, we had u of x equals minus k divided by x. K is a constant. We're looking at positive x, and it looks like this. So that's what should be in your notes, right?
Yeah.
The last thing, exactly. And I had asked that question, what does that have to do? That's gravity, right? That's the gravitational potential. Gravitational potential. And what does that have to do with, I'm just gonna write here, what about u of x equals mg x, which is what we have when we're here near the surface of Earth. Okay. Anybody know how to reconcile those two? They look very different. Okay. But there is a nice reconciliation of them. So what I'll do here is talk about Newton gravity explicitly. This is going to be a major topic later in the semester, but this is something you guys have seen before. You guys may remember if you had two masses separated by a distance r, then what was the law of gravity between those two masses?
G large mass, small mass over r squared or something.
That's right. So, in fact, I'm going to go straight to large mass, small mass. Actually, it's arbitrary masses, but if you're thinking of the Earth and a satellite. So what we had was F of r is equal to G, well, I'm going to write M1, M2 for the moment here, over r squared. That's the celebrated inverse square law. And then by the calculation we did last time in one dimension, and this is actually one dimension as well, or yeah, one variable. By the same calculation we did last time, we would say, okay, we get minus G M1, M2 over R. That would be the potential energy. And we already said, well, in one dimension, at least we have conservation energy. That was the potential energy, U of R. I'll go ahead and write U of R here. And this is between two masses, but this is supposed to be universal gravitation. So if it's universal gravitation, and the proof for spherically symmetric masses comes later, possibly even just next semester. But yeah, if it's universal gravitation, then we can look at it this way. I'm standing anywhere on Earth. Down is towards the center for, for ease of interpretation. I'm standing right there on top. Okay. So this is a body of radius capital R and mass capital M. I've got the lowercase m mass. So what we have here is the force with which the Earth attracts me towards its center is equal to G M M over R squared. Is the radius of Earth. We talk about radius of Earth. So we have number 4. Okay. On the other hand, so that's Newton's law of universal gravitation. On the other hand, I'm up here standing on my bathroom scale. What do I measure? I measure my weight, which is mg, lowercase mg. Okay. So universal gravitation, my weight what do we get for lowercase g here? We just cancel m on both sides. So gravitational constant g, mass of the Earth, radius of Earth squared, is equal to what we otherwise call g. And has anybody ever plugged those numbers in on the left side here to get 9.8? Let's make that a homework assignment, just for the, just to have done it. So for the homework, you just look these up in a book. Look up the mass of Earth, the gravitational constant, radius of Earth, square it, and be amazed that you end up with 9.8. Okay? 9.8 meters per second squared. That's important. So homework, plug in numbers for star, and that is star. Okay. Just to see it in real life. Yeah. So that's part way to our goal of the reconciliation of these two formulas. Because now we know what k is. So I'm going to leave the graph on the left up and erase this stuff right here, okay? I'm going to leave that up, erase this. And see, we've got the value of g now in terms of these things. So let's once more, okay, so we're going to erase this. Okay, here we go. So what's the next iteration of this? So now we have, all right, for Earth, we're going to just keep measuring x from the center of Earth. We have u of x equals minus gm over x. That's the new expression there. And what we're going to do is expand this in a Taylor expansion. In fact, if you're in if you're in math methods, we've actually done this as a homework problem. But let's just go ahead and write this out carefully. So now expand u of x about x naught, which is going to be the radius of Earth. So what we'll have is u of x is equal to u of r plus u prime of r x minus capital R. And we'll do one more plus 1/2 u double prime of r x minus r 20 squared. Right, those are the first terms of the Taylor expansion. That's all we need. Let's go ahead and take a derivative or two. So we have u prime of x is equal to minus gm, x to the minus 1, so minus 1 x squared. We have u second derivative of x equals, this is a plus sign, so we have minus 2gm over x cubed. So that's enough to work with. And now we're going to have, for this thing up here, u of x is equal to minus gm divided by r, got a plus sign, gm my bad, I'm going to put a lowercase m right here. I was mixing up potential and potential energy. potential energy has the mass right there, okay, as we had before. So we can easily make that up. There we go. And so now we're back in business, plus sign G M over R squared. X minus R. And then minus the 2 is going to be canceled with that 1/2 there. So minus G M over R cubed X minus R squared. So that's enough. Plus and so on. So right under here, let me go ahead and deliver the final result. I'm even going to leave the argument out for the moment, okay? This here, I'm just going to say is a constant. Because we know that potential energies are significant up to an arbitrary constant, right? So I'm just going to, this is an arbitrary constant. This next one, what am I going to replace this with? 4 lines back in your notes. This is going to be mg times x minus r. And then I'm just going to write plus small. When are these last terms small?
When R is really big and is being cubed at this point, so we can reasonably say it doesn't affect the outcome.
Yes, so in particular, when x minus r is much, much less than capital R, that's the criterion. And this x minus r is our distance above the surface of Earth. So if we're even, 100 kilometers over the surface of Earth, and the radius of Earth is several thousand kilometers, then that is still a small quantity. So yeah, the more we study Taylor expansion, the more we see what's going on here. And this is the small quantity above the surface of Earth, which I just have to rename, okay? Like MGY, that's the way we always were talking about this before. So that's how we reconcile these two. And graphically, what I've just done is, this is my minus k over x naught. What I've done is I've expanded, I've just got an arbitrary constant. This is the equation of a straight line, small quantity. And you'll recognize we have been doing that in mathematics, right? It's exactly that problem. And so this next term would be the correction term. He said, okay, what if I go 500 kilometers off the surface of Earth? Yeah, then I'm going to have to include this one here to get a more accurate picture. But otherwise, this is just the linear expression. Call it mgy if you want, okay? Or mgh, the distance above the surface. So yeah, let's make sure this distance above the surface. Above the surface. So yeah, we have a nice concrete example. When we do, in just a more general case, we'll leave the letter K there, but we know that we can relate that to gravity, above the surface of Earth, and we can even relate it to this form of gravity here. Okay, good. Let's see if we have anything else there. Just to make sure, since I see I made a little error there earlier, what we have is G is equal to GM over R squared, right? MG is equal to GMM over R squared, right? So check your notes. I may have biffed it there a couple times with the math I did there, but I added it again. And that homework assignment was to just plug these in and make sure you get the good old 9.8 meters per second squared. Okay, so we have that, and now we want to go back to doing dynamics with these things. This was just a nice tangent to put it all into perspective. And I'm even going to return to that problem we discussed last time with the friction, that contrived friction law square root of velocity. Just because I want to add part of that as a homework problem. Then we'll get into the actual energy conserved dynamics. These pens are tenacious. All right. So what we'll do is we'll call this little review section review of separation of variables. Separation of variables. Okay. And the example was m dv dt minus k v to the 1/2 power. So what we had done, I'm going to write this out in two ways. So dv dt equals minus k over m. And remember, I had used the chain rule to get v times dv dx equals minus k over m v to the 1/2. So this one was solved last time, and we used it to find the total distance traveled by this, we've got this object here that we give a push on the x-axis, and it comes to a stop. That was the discussion, it comes to a stop. What I was thinking is we could also do this. So this one, I'm just gonna write here, find v of x and total distance traveled and this is in your notes, but it's worth doing again and writing up. Here we're going to find v of t. And with that we can find the time it takes to come to a stop. And time to come to a stop. Okay. So yeah, we'll make both of these on the next homework assignment. This will just be a review, but I like putting one of these on the exam. Okay. This type of problem where you just do a rudimentary separation of variables and all of the stuff you can discover, where time to come to a stop, distance traveled. Sometimes they get interesting. Depending on the power you choose, you can find one that never comes to a stop, right? The time goes out to infinity to come to a stop, and yet it only travels a finite distance. That's kind of interesting, right? That's the kind of thing you'll get in an interesting calculus problem. So anyway, yeah, let's put that up there as a homework as well. I like assigning one of those on the exam. And the separation of variables technique is good. And we're going to take that to the next topic here. We're back to conservation of energy. So just to review, when we have f is purely a function of position, then we have the potential energy well defined, f, not f prime, f of x prime dx prime a to x. So then we have the potential energy function and 1/2 m x dot squared So you've actually gained a lot already, because Newton's law is a second order differential equation, but this is a first order differential equation. So this is referred to as a first integral of the equations of motion. Energy is a first integral, that's just a form of piece of jargon, so to speak. First integral, or first integral of the equations of motion. So that's what the energy is referred to as. This is the constant. And we can do a lot with this now. First of all, we can just use this as a solution of V as a function of position. Okay. So the one thing we can get is that it's the velocity as a function of position. And yeah, we'll go ahead and even solve it here. So we've got the V, which is dx dt. And good, we've got 2 over m e minus u of x, take the square root. And we have a plus and a minus sign. Right, just when we take square roots. So what's the significance of the plus and minus signs? They're just there along for the ride? Or do they have some meaning?
Direction, I suppose.
Direction, exactly. So you could have a plus sign, if you're on an axis here, you could be moving to the right, or you could be moving to the left. So the plus and minus sign tells us about the direction. And let's go back to our gravitational example. We've just been talking about that. So one-dimensional gravity. And we'll go ahead and plug and have a look at that. So this example, what should we use first? mgx. Then we're going to go ahead and plug in here. Plus or minus the square root of 2 over m. What we can do, for example, we need some constant for that energy. So we'll go ahead and do mgh minus mgx. That should simplify nicely. M's canceled, g's common. What do we have here? Got plus minus 2g h minus x. So we built in a bit of physics into this one now. So the maximum value that x can take is h. That's how far the thing went if we launched it. If we threw a ball straight up in the air, this was its maximum energy that it could have when it got up to the top. And on the other hand, since this is constant, when x is equal to 0, you've got this 2gh, root 2gh. And there's a plus minus, that could either be the speed it has on the way up, and the minus sign would be the speed it has as it's coming down. Okay. So that's a nice example. Let's go ahead and call this for a vertical launch. With V naught equal. So what is this V naught for the vertical launch? It's root 2gh. Something we just had out of the law of free fall the other day. And like I said, plus and minus side, they're headed up, we're coming back down. When x equals h, it comes to a stop. So that's pretty good. We've got the v of x. Now what about u of x equals minus k over x. I'm gonna draw our graph here. I can always help us out here. So now we've got u of x equals minus k over x. So what's the interpretation there? Well, we're just going to go ahead and see what happens when we plug in. Plus minus root 2 over m. Now we don't have a value for the e yet. E minus negative k over x, so e plus k over x. Here's an interesting one. What happens if I let x go to positive infinity here?
You get 2e over m.
Yeah. What is that? What's the interpretation with my vertical throw? You guys may remember this from physics 4a. If I let x go to infinity, okay, this thing goes away. I've got 2e over m. Apparently, this thing is going out to infinity and it's got some speed left over. So I've launched it with an initial speed greater than the escape speed. So that's how that's going to play a role. On the other hand, if I have the minus sign and I plug in k over, say, the radius of Earth, what's that speed? That's the speed of that asteroid collision that's coming in from infinity. So there's a couple of interesting things going on here. And in fact, if you want to get a v equals 0, okay, if you want to get a v equals 0 at some finite x here, then you're going to have a negative energy. But if we look on this graph, we actually have negative values of the energy corresponding to finite distances. Say this is my energy, goes out to there, right? If I had a positive energy, I was just going out to infinity, never coming back. Okay? So we're going to have here, and when we do the central force problem, we'll talk about this a lot more, okay? But it's something that's already apparent here. So, positive E implies motion out to infinity. Negative E implies what we call bounded motion. Bounded motion. Bounded motion. And then E equals 0, which is the boundary between those two. E equals 0 implies escape velocity. Escape velocity for an initial x of 0. Initial x of 0 that's positive, of course. You guys remember that escape velocity when you had mechanics, physics 4a? We'll have to return to it. Doesn't look like you guys remember that one. That's the difference. See, this one here, you can throw it as hard as you want. It's always coming back. This one here, you throw it hard enough, it never returns. So, escape velocity, important. Okay, good. So this is the kind of thing we can get with an analysis of this first integral of the motion here. We can actually get quite a bit of information. Let's see, I want to make sure we have something. Yeah. We'll make this a homework problem. problem here. So for Earth, what do we have here? We have u of x. We decided that was going, and this is the distance from the center of Earth. U of x is equal to minus g mass of Earth, lowercase m, divided by x. And we have 1/2 m v naught squared plus u x naught equals 1/2 m v squared plus u of some other x. Right? That's conservation of energy. By the way, it's always a good way to set up conservation of energy. Just really explicitly take it step by step, okay? Until you get the hang of it. So here, what we're going to have is suppose v goes to 0 as x goes to infinity. B goes to 0 as x goes to infinity, this turns into a 0, and this turns into a 0, right? So then you have x naught equal r, which is radius of Earth, and then calculate the escape velocity and find v naught equals the escape. This is the kind of stuff you can look up everywhere, but you want to go ahead and take this sequence. In particular, you've got this, what we just talked about, we have homework on. And the argument here is very important. V goes to 0 as x goes to infinity. So the right side of this is 0, and now you go ahead and plug in your values and you find the escape speed. Escape speed is important. Yeah, I mean, this is really small and just something to fill in, but it, it'll lead you through some important processes here. Now these are enough for us to do some integration on this. Okay, so this time we're going to set up the conservation of energy expression. So again, we're going to have 1/2 m, and this time I'm going to go ahead and write it out this way, dx dt squared plus u of x equals e. So we have plenty of examples of this. This time we're going to do the separation of variables on this, okay? And the separation of variables is going to give us the following. We've got the dx over dt, we've been looking at 2 over m e minus u of x square root plus minus. So yeah, what would we do for separation of variables? We have the x's on one side and the t's on the other. So we have something interesting, dx divided by, and I can put the plus minus here, 2 over m e minus u of x equals dt. And you can see if we integrate both sides, we're getting an interesting function, namely this here, we can just do 0 to t. What about the left side here? I'm going to go ahead and write it this way, x naught to x, and these are now integration variables. So this isn't what we're looking for, you thought, in mechanics, right? We want x of t, and what we found here is t of x. Okay? You could say that's an intermediate solution. So we're not quite there yet, but we have t as a function of x. And this is actually an important process. In more advanced mechanics, sometimes this is as far as you can get analytically. And then you say you've reduced the solution of the problem to a quadrature. Doesn't mean you're necessarily done, but it's as far as you can get analytically. Because to do this integral, you have to have a nice function u of x that allows you to get an explicit solution. Okay. Otherwise, you could be stuck here, and then what would you do? You'd have to start just analyzing this integral and finding out its properties, without being able to write it down and say sine, cosine, x squared, or whatever. Okay. So this is referred to as reduction of the problem to a quadrature. So just so you've seen this word, a quadrature, and that's just the traditional word for integral really. Quadrature. But there's a couple of really interesting cases where you just are satisfied with this integral here. And I think I'm going to formulate it right now while we've got time. Yeah. Let's see. Best way to tackle this. There are some classes of functions for which we can deal with this. So I've got these 10 minutes. I think we'll look at this general case. One thing we could do, without going through this whole thing, suppose we do have u of x is equal to mgx. We'll just discuss this without actually running through the whole calculation. Can we do the integral 1 over the root of x? Just so you know, 1 over root of x, in fact, we can, right? Because the antiderivative will be something about the square root of x in the numerator. So then we could actually have t having something to do with the square root of x. That makes sense? So there are cases where we could actually do this explicitly. T square root of x. We know that for free fall, we could say, h is equal to 1/2 g t squared. And if we solve for t, what do we get? 2h over g square root. And that h could be the height, our x. So you can see how this would work in some cases. Oh yeah, we don't have to actually go through the whole program. You can see that we have square root of x there, we do the antiderivative, set up the boundaries, and we're going to get the time. So we could use it to get the time of free fall. But a really interesting case that is non-trivial, and we'll set this one up now. What is the time it takes to fall into a center of Newtonian gravity? If you're released from rest. So now, we're really far away from, say, Earth, so that Earth itself is like a dot. We're out here at the distance L. Okay, on Earth, just to be concrete, this is Earth, and I'm an asteroid way out there somewhere at rest. Released from rest, what's the time it takes to fall into the center of attraction? Asteroid. So release from rest, release from rest at x equals L to fall into the center of attraction. Fall into the center of attraction. I want to make that a homework as well and set it up. This is a good one. So everything we need is or was on the board. So what do you guys think? Does this make sense? You know, Newtonian gravity, the Earth's really far away, so essentially we're falling into a dot. Out beyond the moon, right? Falling into something small. And we release this from rest. So Newton's law of gravity says there's going to be some attraction. As it comes closer, it's going to pick up speed. And once it gets to the center, you know, kaboom, where it gets close enough to Earth. But there's a time involved, and how long does that take? So that's one we couldn't guess from this law here. This law doesn't cover that. Right? This is beyond that. But yeah, let's set this one up. So actually, you could say, well, the time is this integral if I set it up right. You know, I could say I'm falling, you know, towards the Earth, so I'll probably take the minus sign for negative velocity. I'm releasing it from rest at L. It's falling into 0, and I have to plug in my energy and my potential energy, my energy, and yeah, my potential energy function. So good. This is a really nice problem, and we're just going to set it up systematically. So since all the ingredients are here, what we need is, you know, 1/2, we're going to do the conservation of energy this way. 1/2 dx dt squared t equals 0 plus u of x0 equals 1/2 m dx dt squared plus u of x. We need that to find out the energy. This of course is the total energy. So what's the energy when I'm at rest? Here it's complicated, it's moving and it's at some undetermined position. But when I'm at rest, I've got a 0, right? And here I have this negative k, we're using k, right? Yeah. Negative k over L equals E. So what this tells us is that is our value of the energy that goes into the integral. So that's how we find the energy.
Does K represent you?
K is going to be the gravitational constant. You know, K is going to be the, remember we had U was equal to negative G M over X. But we're just gonna keep using the letter K. We don't have to write down as much. Right. So yeah, that's where that comes from. Yeah, so that goes in there. And then you're left with a challenging but not impossible integral. Very interesting one. So we'll start with that next time. We'll do some more of these quadratures. But this one I wanted to get set up right away. Give us plenty of time to think about it. Because what I'm going to do next time we meet, for certain types of potential energies, we can we can pull all kinds of constants out of the integral and make the integral dimensionless. That's the preferred way of doing a problem like this. But we'll do that next time, dimensionless. Okay, good. That's all we've got.